Thanks so much for showing interest in this course, Information Theory. Now, you're probably wondering, what is information theory? Well, before I explain what it is, I'm going to ask you a few questions. What do the following subject areas have in common? Thermodynamics, signal processing, chemical engineering, mineral processing, logic games such as Mastermind, Cluedo, Battleships, political campaigns, management structures, jury systems, genetic modelling, gambling, many other subject areas. Now, the ones on the left are a little bit more obvious to give a hint. And if you need more of a hint, maybe look at these logic games such as Mastermind, Cluedo, and Battleships. Well, they can all be set up using a probabilistic system. And when we try and play those games, we don't really know what the answer is. We're trying to update it with information and trials. And yet we have a method in our brains for plausible inference. We can work out what most likely scenarios are. This concept of plausible inference can be described mathematically. However, that mathematical methodology is not really taught at university, not in many subject areas. And I would say in some universities it's not taught at all, and in some universities it's taught a bit. That's what information theory is. It's a mathematical framework for plausible inference for problems that can be represented as probabilistic systems given available information. A more specific mathematical definition, a method to maximize the entropy of a problem, as defined by its probabilistic system, using available information, and by doing so, determine the most plausible solution. So, visual representation of information theory, we have a problem, we represent it as a probabilistic problem. We look at the available information to use a model called maximum entropy, and we're not going to discuss that in this overview, but that's the core of information theory, and it gives us most plausible probabilities and we get a solution. But at no time do we get the exact solution. We're getting a plausible solution. So what's this course about? It teaches you the mathematical foundations of information theory. I explain its historical development. Information theory already exists, and I don't think I've changed the title, but I have changed the context. So it's a new branch of mathematical modelling, started about 50 years ago, but I'm in this course focusing on its extensions to a variety of problems. So, course content briefly, we discussed probability theory as a basis of information theory. Entropy, as you're probably aware, first was used as a term in thermodynamics, so I discussed the thermodynamic perspective. Having said that, you don't need to be a chemical engineer or physicist to understand this course. I'm actually trying to break away from the thermodynamic definition of entropy, but providing you a historical reason for it. My background is mineral processing, so this came about largely because I wanted to teach information theory for mineral processes, but I do provide other applications. Now, in those other applications, we have games and puzzles. So they're actually easier to work on because they're more constrained in their rules and the solutions become clearer. So I put to you that if you can understand games and puzzles, you can certainly understand the thermodynamics. And even if you're not a mineral processor, I don't do complicated problems. You'll understand the mineral processing problems and the relevance, including chemical engineering. You shouldn't necessarily go into this course wanting to understand everything, but to understand that which is most relevant to you. So there could well be people who will participate in this course who are only interested in it from a thermodynamic viewpoint. But the target participants are all mathematicians. You can't be a mathematician and not be interested in this course. Or physicists, because entropy, information theory, are the foundations of thermodynamics, which in turn leads to quantum mechanics. Or mineral processes. This contains so many methods of analyzing mineral processing data which are not currently being used. And or machine learning experts. Now, information theory provides a basis for machine learning, a style of machine learning, which will be made available in future courses. Other participants, electrical engineers, chemists, data analysts, and good mathematicians who are about to start university. This will give you an enormous advantage over your colleagues when you go to university. Prerequisites, well, you've got to have maths. So you've got to be able to differentiate. You've got to understand matrices and vectors, but we're not doing that in much detail. I explained briefly what Lagrange multipliers are. It's a form of optimization of constrained problems. I don't go into it in depth. But it's not complicated and we don't do it in detail. We don't need to. Excel skills. Well, I've provided various Udemy courses to give you those skills if you need to do them. But I'll be explaining VBA functions, name ranges, arrays, and solver. I'll be doing it briefly, yet there are other Udemy courses which go in more depth. What you're going to get out of this course, a deep understanding of the basis of information theory. You'll understand how information theory and entropy is applied to thermodynamics, an understanding of how information theory is applied to a variety of applications, an understanding of how information theory can substantially improve conventional mineral processing chemical engineering methods, and a prerequisite understanding of applying information theory to machine learning. Well, that's it in a nutshell. I really hope you participate. This is going to be one of the most interesting courses you'll ever join. I look forward to seeing you in the course.